Welcome to Study Loop.
All right, hello. Today we'll be talking about more Lewis structures. Specifically, we'll start with this molecule here, which is phosphorus trifluoride. And as usual, the first step with drawing any Lewis structures is to first determine our central atom. So once again, that's going to be the one that's in the lower group. So if we look at phosphorus, we look at fluorine, we see phosphorus is in the lower group. It's going to be in the middle. We will arrange our fluorine molecules around it like this. Then we draw a single bond between P and the three Fs, and that accounts for 6 electrons, as we know. We're also going to then count our valence electrons to see what's left to be put in lone pairs around the atoms. So we know that given phosphorus being in group 15, phosphorus has 5 valence electrons. And then fluorine being a halogen will have 7, but there's 3 of them, so we have 3 times 7 equals 21 valence electrons. So we have a total of 26, and we have 6 taken care of in bonds. So we have 20 lone pair electrons, which I'm abbreviating like so. All right, so let's distribute them. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if you are just keeping track of what we drew in the lone pairs, we have 6, 6, 6, 18. We have 2 more left. And so because we've pretty much completed the octet for all of the 3 fluorines, we need to put those remaining 2 on the phosphorus here. So now let's do one cross check to make sure that everything has an octet and we're good with our number of electrons. So we see, look at phosphorus, we have 2, 4, 6, 8, all set there. 2, 4, 6, and 8, good. 2, 4, 6, 8, good. 2, 4, 6, 8, all set. We have octets and everything, and we have 26 electrons because you can count the bonds plus the 6 lone pair electrons in each of the fluorines. So that's 8 for each of the fluorines. That gives us 24, plus the lone pair here on phosphorus. That gives us 26. And the reason I don't count the total octet for phosphorus is because those electrons have already been accounted for when we talk about fluorine, because if you remember, each of these bonds represents 2 electrons. So you can, I think the easiest way to think of them is as if they're being shared, right? That's the accurate way, that these 2 electrons here are being shared by both of them. But you can count them as being part of one or another and just keep track of that to make sure that you don't double count. So there's multiple ways to count it. I prefer to kind of do this grouping of the peripheral atoms and then just count the lone pairs or whatever else is left in the central one. That allows you to not be caught up in forgetting or keeping track of extra things. All right. The next example is carbonic acid. So I'll do that here. That's H2CO3. Now, this is an example of a situation where you may have multiple central atoms. And also, I should mention that in the premise of the question, it does say that both H's are attached. Sorry. Attached to oxygen. All right. So with that in mind, we can put our carbon in the middle because it does have the lowest group number, and we know H can never be a central atom because it only forms one bond. So, and then we can put our O's in a pattern around the C like so. Remember, just going back up to our periodic table up here, we can see that carbon is in a lower group than oxygen and therefore is going to be in the middle in this situation. Okay, so now we have this. We can also draw in our hydrogens because we know that they're going to be bound to the oxygen. So we can put them anywhere because remember, Lewis structures don't tell us about 3D structures. So we put them here, all set. Okay, now we can then continue as normal, draw the rest of our single bonds like that. Now we figure out that since each single bond counts for 2 electrons, 2, 4, 6, 8, 10, we have 10 total electrons just accounted for in the single bonds, plus in single bonds. And we also now want to talk about how many total valence electrons we're supposed to have, so we can count them. We have 1 each on 2 hydrogens, so we have 2 for hydrogen. Then we're going to have 4 for the carbon. And then we will have 6 times 3, so 18 for the oxygen. All right, so we add those, 2 plus 4 plus 18, gives us a total of 24 valence electrons. So if you're from before, we have 10 already accounted for. So we subtract and we see that we have 14 left in lone pairs. Okay, so now we can start to draw them. So we know that our oxygens are going to be the only ones most likely that will have lone pairs. Typically, carbon does not like to form lone pairs because carbon is not a very stable holder, I suppose, of lone pairs. It likes to form bonds. So oxygen, we know because of its high electronegativity, likes to hold on to electrons. So we'll start distributing them on the peripheral oxygens first. So we have 14. So we have 1, 2, 3, 4, 5, 6. That leaves 8 behind. Now we can see we fill out 6 here because we have 2 already in this bond. So 2 plus 6 makes 8. This oxygen is forming 2 bonds, one with the carbon, one with the oxygen. So that accounts for 4 electrons. So we need 4 more in lone pairs, 1, 2, 3, 4. And the same situation here, 1, 2, 3, 4. So if we add just the lone pairs up, we have 6 here, 4 more, 14 lone pairs. Now we can add everything up, and you might notice that there is a small issue here. We have our total number of electrons, and you can count that. You can count the bonds as 2, you can count the lone pairs, and you'll see we have 24 electrons. The problem is that our carbon's octet is not full yet. And this goes back to that 5th extra step where you're going to have to move one of the lone pairs from the one of the oxygens in order to form a double bond. And most likely than not, you don't want to remove a lone pair from oxygen and put it as a double bond, because then what you'll end up doing is you'll be taking away some of the electrons, and that could actually result in a change in the formal charge, which we don't want to do. So typically, you'd be looking at the O here, which has 3 lone pairs, because traditionally speaking, an oxygen when bound likes to just have 2 sets of lone pairs. So we'll move this lone pair over here to form this second bond, and we can get rid of these extra electrons. Now, once we've done that, we can count. We have 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for the oxygen, 2, 4, 6, 8 for this, 2, 4, 6, 8 here, and there's an extra dot here, apologize. And for hydrogen, we just need the 2, which are found in this single bond. So that's what this structure looks like. You may see this drawn a little differently. You may see the oxygen, like the double bonded, the carbonyl oxygen drawn up here. It does not actually matter where you draw that, because remember that this does not represent the true 3D structure of this molecule. All right, the last example of this set is CS2, carbon disulfide. All right, and so once again, as always, we'll start with carbon in the middle because of its lower group, and you can confirm that as above. Sulfur is below oxygen in group 16, and so carbon is in group 14, lower group in the middle. Okay, so carbon in the middle, we can draw our sulfurs on either side. We can then count up our valence electrons. So we have 4 for the carbon plus 6 times 2, 12. So 4 plus 6 for each sulfur times 2. So that's 4 plus 12. That gives us 16 total valence electrons. So once again, we draw a couple of single bonds, and then we distribute the lone pairs, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And just by the lone pairs, we have 12 in lone pairs plus 2 in the bonds, 16 total. But once again, carbon does not have the octet. So we need to then move into having multiple bonds or double bonds. So the easiest way to do this is to move 1 lone pair each, because the group 16 elements like to have just 2 lone pairs. You push these this lone pair to make a bond, push this lone pair to make a bond, and then you basically create 2 sets of double bonds, as here, and you basically take out 1 lone pair. And now everything as an octet